Yes?
What was the point of going that high order of integration?
What is the point of going that high order? Very good question. That is for integrating very oscillatory functions. Integrating function that is has much higher frequency content than sine of x. So for example, if you do instead of sine of x, okay, let's say we still get 10 points. If you do sine of 9 times x, right? So basically you get a bunch of periods, and it's like we get one more positive period than the negative periods. And what is the solution for that? If you split up into 9, if you split up into 9 and 8 of them cancel, I believe it's 2 over 9, right? The accuracy is not that good even with 10 points. Is 2 over 9 the correct?
Yes.
Also yes. Okay. Now if you do if you pick 20, I believe the solution is going to be much better, right? So for more oscillatory functions, you need to have more points. So imagine if you have if you want to do, say, find an element with a single element, right? And you want to use very high order polynomials to approximate the solution as we are doing in the project. That's called spectral method. And suppose you want to compute solutions of, let's say, turbulent fluid flows, where you have a lot of oscillatory contents and there is a lot of small scales, goes all the way to what we call Kolmogorov scale, which is like really order of magnitude smaller than the solution you want to, the physical domain you want to resolve. Then you need very high order integrals in order to resolve, in order to have enough points to resolve all this high frequency content. That's why we go all the way to very high order. Yes?
So why don't we split up the domain and have a finite grid size instead? Like, what's the trade-off between a high order method and a finite domain?
Very good question. What's the trade-off between a very high order method and split up the domain into smaller segments? So the most prominent benefit of splitting up the domain into smaller segments is the ability to handle complex geometry. So we did a two-dimensional Poisson's equation, right, for basically lecture 2 of finite element. And we can see if we split up into smaller segments using low-order polynomials, it's very easy to handle complex geometry. While if you use a global polynomial or anything, global anything, to treat complex domain, people did like years of research into that. But up to now, there is still not a very stable method for treating like whatever type of element you want with just a single element. So being able to handle complex geometry. But if you have a very simple geometry, there are, I mean, like the type of spectral method, basically a single element, a high order polynomial or high order sinusoidal functions, gives you more bang for the buck, which means you can have smaller degrees of freedoms and the solution can be more accurate. So that's the primary treatment. Oh, another thing is if you have solution that exhibits non-smoothness, that's another good reason not to use a global high order element, because things like Gauss quadrature, actually just a polynomial approximation basically is not very good if you have discontinuous features.
If in practice we know, for example, we know we want to integrate the function like f times sinus something on 0, 1, but we know the function only at some grid points, and these grid points are maybe not the Legend Gauss quadrature point. So is it better to try to infer the values of the function, of the discretized function at the Gauss quadrature points and use the Gauss quadrature formula, or is it better to use the formula on each grid points on which we know actually the function we want to integrate?
So I think if you have a finite difference discretization where you only know the value of the function on the grid points. Okay, so if you only know the value of the function at the grid points, so you can do two things. You can interpolate, right, at the Gauss quadrature points, then integrate. So the accuracy you're gonna get is the lower of the order of integration and the order of interpolation, right? If you have a smooth function, there are very good interpolation schemes for smooth functions. So I would, and if the accuracy is important to you, I would go for the way of doing interpolation first and then use Gauss quadrature. If you suspect the function may not be smooth, then I would be very careful, because I mean Gauss quadrature, they don't perform very well for discontinuous functions, but like it's not going to be horrible. But interpolation schemes, they can be horrible if you have functions that are, I mean, high order interpolation schemes. They can give you like ridiculous results if you have functions that are not continuous.